Recall that in a t-test, we start off with two samples. And what we can do is we can create a histogram of the two samples, in this case, red and blue. And along the vertical axis of the histogram, we show the frequency with which the data falls within these little bins or categories. The underlying data, however, is continuous. We just create these ordinal bins in order to create the histogram. Now, when we actually run the t-test, we forget about the ordinal bins and we simply calculate the mean of sample 1 and we calculate the mean of sample 2, and based on some other characteristics of the sample, we estimate the mean of the sampling distribution for one sample and then the other sample, and then we calculate the probability that the two samples are really from the same population. Now consider a situation in which we have categorical data. So here's a histogram, or at least it looks like a histogram, and again, as before, it shows two samples. In this case, cell phone market share in February of 2009 and market share in August of 2009. And as before, on the vertical axis, we have the frequency of outcomes. But the big difference here is along the horizontal axis. These different phone operating systems are not ordinal. We could put them in any order we want. Because they're not ordinal, it makes no sense to say what's the mean of the red versus the mean of the blue, or to situate them on a histogram and try to determine whether one is larger than the other. To do this, we need an entirely different set of tools. This gives us the goal of this lesson. Can we recognize a difference, or a gap if you like, between two samples when the data in the sample is categorical rather than continuous as it was for the t-test? The starting point for our analysis of categorical data is a contingency table. What we do in a contingency table is we identify our two samples, in this case sample 1 and sample 2, and we identify the outcome categories. So we have outcome 1 and outcome 2. And what we're really interested in is the membership in each of these quadrants or each of these cells. That is the frequency in which an observation belongs to sample 1 and has outcome 1 versus being sample 2 and having outcome 1. Now what we can do to flesh this out a little more is then look at the marginal totals. The total number from outcome 1, the total number from outcome 2, and the same for the samples, and of course the grand total. The information in the contingency table allows us to calculate the observed probabilities of membership in sample 1 outcome 1 versus sample 2 outcome 2, as well as the marginal and conditional probabilities, which become much more important later. Now, the practical problem we want to address in this lesson is how precisely does one create a contingency table given the data we often get. So typically the data we get from a database or from some other system is in tabular form. That is, you have columns of data and each row represents an observation. We've called this previously stacked data. What we want to do is take one of the columns and pivot it so it goes across the rows. And then once we have the columns and the rows in the correct format, we enter in the observed count in the cells. The context for the rest of this lesson is the bank data that we saw previously. Recall that we ran a visual gap analysis using a histogram, and it was fairly inconclusive. So then we ran a t-test in Excel, and we found there was in fact a fairly significant difference between the salaries of male and female employees. But then when we looked at the histograms, we saw there were quite a few employees on the right hand, the salary scale, and these people all happened to be men. So that could account for some of this difference. In fact, if we censored those men, saying that they're from a different population, managers rather than worker bees, then the difference between male and females in the t-test basically becomes insignificant. So this leads to a broader question, which is, well, if we don't have gender bias in salary, if we exclude managers, it seems that we may have gender bias in selecting our managers. So that's a very different question. The first step in determining whether male and female employees in our bank data are different in terms of their management status is to create a new variable or a new column called manager. So I've done this here, and all I've done is remapped or recoded job grade. So if job grade, which is in cell C2, is greater or equal to a job grade of 5, then this if function returns the code management. Otherwise, it returns non-management. And that allows me to have a column. Now what I want to do is use a pivot table to pivot manager so it's along the top in a row. So I select somewhere in my data set, hit insert and pivot table, and by default it selects all my data as it should, and then I get my pivot table dialog. Now remember, I want gender along the row, and I want my new field manager along the columns. So if I look over on the left, I've got a good start. The question is, what do I want at the intersection of these labels? Well, I want a count of female managers, female non-management, male non-management. Well, whenever we do a count, it doesn't really matter what we count. So rather than the sum of salary or the average salary, where it really matters what this value field is, I'm just going to drop in the employee ID. Now, by default, it gives me the sum of employee ID, which is pretty useless. So what I do is I click this down arrow, select the field settings, and change it to count. So now when I hit OK, you'll see I get precisely the data I want in a contingency table. So the first question we might ask ourselves once we have a contingency table is, what can we do with it? One of the first things we typically do is we convert the observed frequencies into relative frequencies. So for example, we have 10 females who are in management out of a grand total of 208 employees. That tells us that we have 4.8% of our employees are female managers. Now, the next thing we do is ask, how does that compare? How does what we observe compare to what we expect? So let's say we can calculate the expected relative frequency. And I'll talk about how you do that in a moment. But let's just say for now that we have what we should expect. In this case, we expect 11.3 of our managers will be female, and what we actually get is 4.8. So that suggests that there's some difference. In order to explain where these expected frequencies come from, we have to go back and review a bit of basic probability theory. Let's assume that we have a coin that is fair, and let's say that we flip it twice in a row. Now, 4 different things can happen: head heads, head tails, tails tails, or tails heads. The important thing is that the flip of the first coin in no way influences the flip of the second coin. The two flips are, I hope you'll agree, completely independent. Now, if they're independent, we can take the probability of any one of these outcomes, let's say heads heads, and calculate it by multiplying the probability of heads on the first toss times the probability of heads on the second toss. And since it's a fair coin, probability of heads on the first toss is 0.5, probability of heads on the second toss is 0.5. So the overall probability of heads heads is 0.25 or 1/4, which we can see from above if we enumerate the sample, uh, that heads heads is one of our four possibilities. The important thing is that this little bit of arithmetic, probability of heads on the first toss times the probability of heads on the second toss, only works if the two events are independent. Let's use a slightly different example to illustrate probabilistic dependence. So let's say you're walking down the street and you meet someone, just any old person, and the probability that a person taken at random from society, the probability that person is a professor is, let's say, 10%. And then let's also assume that the probability that a person owns a Volvo is also 10%. So if we assume that being a professor and owning a Volvo are independent, then the probability of professor and Volvo is 10% times 10% equals 1 in 100. But if it turns out that professors, for whatever reason, tend to like Volvos, then those two things are not independent. And if they're not independent, then we can't do this. We can't simply multiply the two probabilities. In fact, if they're not independent, we have no idea what the joint probability of being a professor and owning a Volvo is. We can use this feature of independence to calculate our expectations. So let's say that we have our contingency table converted into relative frequencies. It's a simple matter to go to the margins and see that the overall probability of being in management, irrespective of gender, is 16.8%. And the overall probability of being a female, irrespective of management status, is about 67.3% in this firm. So now if we make the assumption of independence, then the probability of being female and management should be 0.673 times 0.168, or about 11.3%. This is our expectation given the assumption of independence. So let's recap what we have. We have the observed frequency of the interactions of two variables, in this case gender and managerial status. Then we have the expected frequencies of their interaction given the assumption that gender and managerial status are independent. So if we went through and compared all these cells, the observed to the expected, and say subtracted them, we should expect that they would be 0 or very close to 0 if our assumption of independence was in fact true. On the other hand, if we had huge differences between observed and expected, then we would say it's more unlikely that the two variables are independent. Well, it turns out, not surprisingly, that we have a statistic for this. It's called the chi-squared statistic, and you don't have to worry too much about it, but it conforms to a chi-squared distribution that's centered at 0. So what this means is if we calculate the chi-squared statistic for our observed and our expected values, and it's very close to 0, then we conclude that the two variables, in this case gender and managerial status, are in fact independent. Now, on the other hand, if we get a huge chi-squared statistic, then we're less certain about this independence assumption, and we would conclude that the two variables are dependent in some way. We don't know how, but they're certainly not independent. So what I'm going to demonstrate now is how to do this chi-squared test of independence within SAS. As in Excel, our data here is in a very standard database format, meaning it's stacked. So to create a contingency table, we have to do the exact same thing we did in Excel. We have to pivot the data. Now to do this, I go Task, and then under Describe, there's a thing called Table Analysis. So we get a wizard, and we basically have to tell it which two variables do we want in the table. So we want gender and manager. So that's the data part. Then we click on Tables, and we define the table. So we put the top one up first in this version of SAS Enterprise Guide, manager, and then gender along here. And I'm just dropping it along the left side of that graphic. The next step is then to say, well, what do we want in those cell statistics before we showed the count of people in each group. So I'm going to do that again. I'm just going to show the cell frequencies. I'm not going to show the percentages in order to keep it clean. And I'm not going to worry about my table statistics or anything like that now. I'm just going to start off with the contingency table. So when I run this, it goes away for a little bit, and I get exactly what I had in Excel. A very simple contingency table with my totals and my marginal totals. Now if I want, I can hit Modify Task and go back and make some changes. For example, in the cells, I can show the cell frequency, and I can show the expected cell frequency if these two variables, gender and whether or not the person's a manager, if they're independent, it'll calculate what it would expect to see in those cells. So if I run that, we get what we had before, is slightly lower than we would have expected, for example, in the female management quadrant. So we can also add a lot more information to this very easily. We can show the percentages, we can show the column percentages, the row percentages, and you can play around with that. But after a while, it gets a little bit harder to read. But that's a good start, and that gives us the contingency table that we need in SAS. When we look at our contingency table, it's pretty clear that our observed frequency of employees in certain quadrants is very different than the expected number of employees in each quadrant, given the assumption that gender and managerial status are independent. The question we ask now is whether they're different enough. So what we're going to do now is we're going to modify this table analysis task to actually give us an independence test. So what we're going to use, there's a lot of different ones out here, and if we were doing this for a living, we'd know which one to use, but we're going to just use the chi-squared test of independence. Very simple, very straightforward. So we run it, and what it gives us is just a little bit more information. So if we go down to the bottom, you see it runs all sorts of different variations of the chi-squared test. Fortunately here, they're all giving us pretty much the same result. The p-value is over here on the right. Now, the p-value here, just like every other time we do hypothesis testing, is the probability of the boring thing. That is, our null hypothesis in this case is that gender and managerial status are independent. What the p-value tells us is the probability that that assumption is true. So in effect, we look at this and we say we're pretty certain that managerial status, and gender are not independent. We don't know how they're dependent, and there can be many different forms of dependency, but there's only one form of independence, and it's extremely unlikely, given these vast differences in every cell between observed and expected, that these two variables are independent.